The invention of 10 gig gave us an interesting dilemma. We had servers at the time with probably 10 to 12, maybe 1 gig connections per server, which is a lot. And we'd look at that and say, okay, well, how many 10 gig interfaces do I need? Because I only had 12 gig total going to it, so maybe throwing two 10 gig connections should be enough. But the hypervisors like multiple disparate connections. And I can't afford, because my 10 gig switches were expensive and each port cost a lot of money, I can't afford to put 10 or 12 10 gig connections up per server. Well, Cisco invented a technology called Virtual Interface Card, or the VIC. And from that, we can create virtual NICs in our environment, meaning we can take two 10 gig connections and turn them into a lot of 10 gig connections within the virtual space. In this video, we're going to dive into that technology and see how it works. Now, why do we care about having multiple connections per server? Why not just run two connections? That's a great question. And in order to dissect that, let's just kind of draw out a virtual host here and bring in a bunch of physical connections. This is my host here, whether that's running VMware, Hyper-V, KVM, XenServer, whatever hypervisor I'm running, this is my virtual host. All of these hypervisors run the same networking concepts. When I bring the virtual or the physical network connections into the host, I have to terminate them on something called a virtual switch. And the reason for that is I have a lot of different virtual machines in here. And each virtual machine has its own virtual NIC, in a way, where it's a different virtual NIC, but it has a NIC on the virtual machine that has a MAC address. And if we think about it, if we have two virtual machines, or four virtual machines here in our example, that are all communicating out to the network, a network switch, let's pause a moment and think about this, a network switch can't bring a packet in to one interface and send it out the same interface. So if two virtual machines want to talk to each other on the same switch, or I'm sorry, on the same virtual host, we can't actually send that out to the network. It won't work that way. So we have to be able to switch internally. So we have a virtual switch that allows these virtual machines to communicate to each other, because even though it's all one host, we're actually connecting on two different virtual connections. See, the virtual and the physical world, they start to blur a little bit as we dissect this and take a look at what's going on under the hood. Now, each virtual switch is where we bring in the physical connections. So these physical connections are terminated onto a virtual switch. So I might have three different virtual switches in this environment, and I'm going to configure all of these physical interfaces to terminate onto these virtual switches. And so traffic from the virtual machines on the left, they'll go out one of these two interfaces, and the virtual machines, let's say we connect these up to, we'll just add a fifth virtual machine here, and same thing over here. So the middle two virtual machines are going to go up those physical interfaces, and same thing with the virtual machine on the right. So I have three virtual switches. Why not just bring everything into one virtual switch in the middle and have all of our virtual machines connect into that one virtual switch? And the reason for that is we want to separate different traffic types. For example, we might have a live migration connection over here. This is called a VMK, or VM kernel port. And we run the live migration. If we want to move virtual machines between hosts, we run that through a particular virtual switch and out to the next host. Now, the hypervisors, they like that to be separated, for example, from a virtual switch that maybe runs the management. So the management of this host would be tied to a VMK on a different virtual switch. Same thing with storage traffic. We have to worry about iSCSI. Security folks might really be happy with the idea of having a separate virtual switch for our DMZ. And so we can start to see that there's very good reasons for having multiple virtual switches in a single virtual host. But in order to have multiple virtual switches, that necessitates multiple physical connections. We have to have those physical connections in order to have a virtual switch. So again, we go back to our example. We don't want to consume 10 switch ports on the upstream switches with each one of these. We might run out of switch ports. Our nice new 10 gig switches when we're out of switch ports. Now, 10 gig used to be a lot more expensive, and these days it's not that bad. Maybe we have plenty of 10 gig. But what about 40 gig? What about 100 gig? I mean, we're going to have this problem regardless of the current state of affairs, because we're always going to be pushing towards the higher bandwidths. And so we might have a host with 6 10 gig connections or 8 10 gig connections, and today we can handle that. And then our networking team, we procure new 40 gig interfaces on our switches. Oh, we're going to take advantage of that. But again, same problem. We're really going to put 10 40 gig interfaces? that would be a bad idea just from an expense perspective. We've got to have a better solution for this. And that's what Cisco did when they created the virtual interface card. So let's take a look at how that works. Cisco's card goes into a server, a UCS server. It has to be UCS, by the way. They don't make this for other server hardware vendors. And the VIC it interfaces with the network. So we bring our big fat pipes in here, whether they're 10 gig connections or 40 gig connections. They have VICs that support both. And the hypervisor level, this is going to look kind of funny because we're going to nest the hypervisor in here. In fact, let's just use a different color. So we're going to draw what the hypervisor sees here. Again, this is whatever brand of hypervisor we're using. Doesn't really matter. It operates the same way for each one. And the VIC creates these virtual NICs. Now, these virtual NICs are configured inside of UCS Manager. We can configure as many as we want within reason. The VIC supports 256. So if we need more than that, we have problems, I think. And from a hypervisor perspective, those virtual switches we talked about, which is, again, where the VMs live and even those VMKs that we talked about, they both connect into the virtual switch. Those now see the virtual NICs as being actual physical devices. And so we, in a way, I suppose we're tricking the hypervisor, but this technology was actually developed by Cisco and VMware in collaboration, and so it fits the best practice mold. So we're not violating any rules here. What we're doing is we're allowing the system to separate that traffic. And the best part is it's within hardware. The VIC is running all of this virtualization within hardware, and Cisco, they know how to carve up traffic. They know a thing or two about quality of service. And so when we deliver QoS configurations to these VNICs, it's respected within the VIC. And so what we're doing is we're taking that 20 gig of throughput, or maybe 80 gig of throughput if those are 40 gig connections, and we're leveraging that upstream. So we're only connecting into 2 physical interfaces within the networking world, and we're pushing down as many VNICs as we need. So again, this is a best of both worlds technology. We get to have fewer switch ports consumed, and at the same time we have as many V switches as we need. The VIC makes it so we don't have to choose anymore between consuming a bunch of interfaces on our network and having the virtual switch configuration that we need. So we can now have both, which is awesome. We do that by leveraging virtual NICs within UCS Manager. We're going to configure those on every single server and decide how many we want and deploy that down so the hypervisor can have the configuration that we want it to have. I hope this has been informative for you, and I'd like to thank you for viewing.